Hello and welcome to the fourth and the last lecture in chapter 21 of our comprehensive course on AI, ML and DS. Now here we want to talk about non-parametric statistical methods. Now why non-parametric methods are important or where they become more important? We have seen various parametric methods for hypothesis testing, that is single sample t-test and two independent sample t-test and paired sample t-test and ANOVA or F-test and Z-test and then maybe the chi-square test and all. But they rely on one basic assumption. The assumption is that the data distribution is like this perfect normal distribution or bell curve. Okay, because all these tests rely on central limit theorem, and central limit theorem has this as the basic assumption that this data distribution is normal. Now the question is what to do if data distribution is not normal, and you will encounter such distribution several times. In fact, we have seen several different types of distribution, and we know that there is often a case where distribution is skewed in one direction, like this lower graph, right? So at that time it is not normal, and rather than forcefully bringing it to normality by cutting off a few variable and say I can cut off this many variables and I can consider the rest of the data points as approximately normal, but that are all kind of distorting your original data. So instead of that, why don't we use some methods which are applicable to any type of data distribution? So the non-parametric methods are those kind of methods only which can be applied to any type of data distribution. So they do not assume specific distribution of data, and they are particularly useful when you cannot assume that your data follows normal distribution, which is common assumption in many parametric tests. So what is the importance? Clearly, these methods are more flexible because they do not require the data to be normally distributed, and that means they can handle both these types of data. They can handle normal data also, and they can handle, that is this upper normal data also, and they can handle this lower non-normal data or skewed data also. Okay, that is one thing. And therefore, as far as skewed data is concerned or ordinal data is concerned, where some inherent order is there, for example, there is some data set in which employees of an organization, they are ranked like this: junior clerk, then senior clerk, then assistant officer, then officer, then assistant manager, then manager, then vice president, then CEO. Now clearly here there is some order implied. Okay, so at that time this kind of data is easier to handle using this non-parametric test. Okay, and they are also useful with small sample size, because one other requirement for using central limit theorem is that also that the sample should have minimum at least 30 members or records. Okay, so greater than or equal to 30 sample size is required for this normal distribution. So we, for the central limit theorem, but what to do if sample size is small, say only 10 observations are there or something like that? So at that time you can use this non-parametric test. Now there are as such many non-parametric tests: Mann-Whitney U-test, Kruskal-Wallis H-test, and Spearman's rank correlation. But we will not do this Mann-Whitney because you will see that Kruskal-Wallis is just an extended form of Mann-Whitney test. So that means it is a more generalized form. So Mann-Whitney test is used to compare differences between two independent groups when the dependent variable is either ordinal or continuous but not normally distributed. Okay, so that means that you have to think whether which kind of variable is that. Okay. So if the dependent variable is ordinal, I gave an example of ordinal variable, or it is a continuous variable, so that is just changing like a number 1, 2, 3, 4, and the value between 1 and 2 are also possible, and the value between 1 and 1.5 are also possible, and so on. So constantly changing, then that kind of data, but not normally distributed. So at that time you can use this Mann-Whitney U-test. Okay, and this is useful only for two independent groups. That is its major limitation. But what to do if there are more than two, this kind of groups only, independent groups, and the dependent variable is either ordinal or continuous but not normally distributed. So at that time you have to use another test which is an extension of Mann-Whitney test, and that is called Kruskal-Wallis test, and that is the test for comparing more than two groups. So it can be used for 3 groups, 4 groups, or any number of groups as long as this condition is satisfied, right? Okay, so let us take some, and then we will also talk about Spearman's correlation, because earlier we have seen about Pearson correlation, and that is this one only, heat map and all those things which we plotted earlier, this one. Okay, this correlation, that is Pearson correlation. But Pearson correlation is useful only when the relationship between the two variables between which you are finding the correlation coefficient is linear. Now, there are multiple different types of data for which the linearity assumption is not obeyed. So that time this Spearman's correlation is used. And the difference between Pearson and Spearman is Pearson also gives both strength and the direction of association. That we have seen plus sign if you get in the correlation coefficient. That means as one variable increases, other also increases, positively correlated. And if minus sign you get, that means as one variable increases, other decreases, they are negatively correlated. And bigger the value of correlation coefficient, they are more strongly correlated. That also we have seen. Same thing is applicable here for Spearman correlation also, but there is one important difference. We do not consider the absolute value of the two variables or two features, but rather we consider their ranked value. Now, what is that ranked value that we will see? But first, let us take one example of this Kruskal-Wallis test, and then we will talk about Spearman's correlation. So, Kruskal-Wallis test is used to see if there is a difference in the tips given at different times of the day, lunch versus dinner. So, earlier we did ANOVA for deciding that if the day itself affects the mean value of tip. So we found that no, we rejected the, rather we said that we failed to reject the null hypothesis, or that means null hypothesis which said that whether it is Thursday or Friday or Saturday or Sunday, the mean value of tip remains the same. So that means the day does not affect the amount of tip given. Similarly, here we want to test one more thing, that does the tip in the tip data set depend upon the time at which the meal is taken. So that means is it that people tend to give more tip at the lunch and less at the dinner, or vice versa, more at the dinner and less at the lunch? So again, null hypothesis will be that the time of the day has no effect on the mean value of tip, or that means median value of the tip at the lunch and the median value of tip at the dinner, they are the same. Okay, instead of median you could take mean also, but median here because that is perhaps more robust measure of central tendency. And the alternative hypothesis says that no, median value of lunch and median value of dinner are different. Maybe median of dinner is greater than the median of lunch, right? So that means if that comes out to be true, then we can say that people tend to give more tip at the dinner time. But if null hypothesis is true, then you can say that lunch or dinner does not make any difference. Whatever people want to give as tip, that remains the same. Okay. Now, how to reject this null hypothesis? So again, we will perform this Kruskal-Wallis H test. Now, whether you perform the ANOVA, that is F test or Z test or anything, ultimately you calculate P value only. And if P value is less than the significance level, suppose I have taken alpha is equal to 0.05 for 95% of the confidence interval, then you can reject the null hypothesis. So then in that case, I would say that the tip given depends upon whether it is lunch or dinner. But if P value is greater than the alpha significance level, then in that case, we will say that null hypothesis cannot be rejected, right? So then we take one such example. Also, every test gives some statistics. For example, T test gives T statistic, then that ANOVA that gives F statistic, then Z test that gives Z score. And usually the statistics should be larger in value. Plus or minus sign is okay, but they should be larger in value. Then that means there is a greater chance that P value will be less than the significance level, and that means there is a greater chance that null hypothesis could be rejected. Okay, so large value of here also this test gives another statistic which is called KW statistic or Kruskal-Wallis statistic, and it compares the ranks of the data across the groups. It does not compare the mean, it does not compare the median also, but it compares the ranks of the data across the group. And the larger value of this statistic indicates there is greater disparity between the two groups in terms of rank of the data. And that means such a disparity cannot satisfy my null hypothesis. Null hypothesis says that rank under the lunch and dinner are same. So that I would say that null hypothesis is not valid or rejected, and therefore alternative hypothesis is valid. For example, if Kruskal-Wallis test is done and it gives this, that degree of freedom is equal to number of groups minus 1. Okay, so that means if you are comparing two groups, here you are comparing two groups, lunch and dinner time samples. So therefore the 2 minus 1, so the degree of freedom will be 1. And you get you take alpha is equal to 0.05. Then if you get P value of this somewhere value should be given, right? Then yes, if this Kruskal-Wallis statistic exceeds the critical value. Now the question is how to calculate the critical value. So for critical value, there are again tables or there are some statistical functions which you use. And suppose the critical value for degree of freedom 1 and alpha equals 0.05 comes out to be 3.841. Then in that case, you have to say that if my Kruskal-Wallis test statistic is greater than, significantly greater than 3.841, suppose this test statistics is large, say 12. So then in that case, I will say that my p-value would be significantly less than this alpha, and then in that case, null hypothesis would be rejected. So such a Kruskal-Wallis statistic, which is much higher than the critical value, that would suggest that null hypothesis is rejected. Okay. Now, once null hypothesis is rejected, you also have to see the size of that effect. So suppose you get that, okay, the dinner time tip and the lunch time tip are different, but sometimes if the difference between the two tips is just maybe $0.01 or that is maybe 1 cent. So the question is, yes, hypothesis, null hypothesis is rejected, and that means the dinner and lunch tips are different. But the question is it significant enough from business point of view? Statistically, it is significant enough. Your Kruskal-Wallis test came out to be more than the critical value. But is it critical enough or significant enough from business point of view? Then you may not want to reshuffle the waiters, what you call shifts, just for the sake of who gets 1 cent more tips. Rather than that, it would be perhaps more effective if you compensate the waiter in the shift where tip is less yourself, okay, rather than go on changing their shift, because people demand higher salary for working in flexible or different shifts. But if you keep their shifts the same, then they may be ready to work for a lower salary. So here also the steps are same. First step is importing library. Second step is loading the data set. So if you take it in a different cell, the next step is loading the data set. Next step is the separation of two samples. So one is the lunch sample and another is the dinner sample, right? Okay. So first import the libraries. Now Seaborn, Pandas, they are well known. And from scipy.stats, this time we are importing Kruskal. Okay. And then load the tips data set. Data set is our well known data set that if I view it, then df is equal to this kind of data, right? So it shows that these are in this column, there are the tip amount, and in this column there are time, and there are two categories in the time, dinner or lunch, right? Now I can take lunch tips is equal to, from df, take a subset of df time equals lunch. So we are conditionally taking a subset that df time column should have value, this is a comparison operator, should have value equal to lunch. And once that much is taken, then with that we also take tip, right? Similarly, in the dinner tips we take df, from which I take the subset df time column is equals dinner. So now the value of this time column should be equals dinner. That means this will have only those records for dinner and this will have only those records for lunch. And there also we collect the tip also in one column, and then let us print those two. So lunch tips are these, okay, the records and the tips. And here the dinner tips are these. We are not printing dinner or lunch because this whole data set is for lunch only, that we know. And similarly, this whole data set is for dinner only. We have taken subsets that way, right? So we don't write that, we just write the amount of tip. Now these are two groups. Now I have to find some statistic, say median or mean or something, and I have to check whether this statistic for the two samples significantly differs or not. And this time there is no such requirement that this tips must be following normal distribution. Whether it is normal or not normal, we don't care, because non-parametric test will always work. So Kruskal, lunch tips, dinner tips, and again every test, this kind of test will give two output. So Kruskal is the name of the test which we imported here, okay, and then it takes two in argument. One is the first group sample which you want to compare, another is the second sample which you want to compare. So it contains only the tips. This contains tips for the lunch and this contains tips for the dinner. And whatever result this whole test will give, it will give two results. The one is the test statistic. So you can write it maybe K statistic or just stat. And another is P value. You can give any name, P, Q or A, B, anything, right? So I am writing stat and P value. And then I am printing those values. As I said, this statistic should be much higher than the critical value. What is the critical value? Here there are two samples only. So we calculated that the degree of freedom is number of groups minus 1. So 1. And for alpha 0.05, you can calculate. There are ready-made tables available or ready-made tools online also. That what is the critical value for the Kruskal statistic. So it came out to be 3.841. So now our test is that we want to check what our H statistics comes out to be. And more importantly, okay, H statistic should be greater than critical value, but P value should be less than alpha. So if you do that, H statistic is 4.78. So it seems that it is bigger than the critical value of 3.841. So that means there is enough ground for the null hypothesis to be rejected. And the P value comes out to be 0.028. So that P value is also less than alpha 0.05 because it is approximately 0.03. This is approximately 0.03. And that means you can say that P is less than alpha. So this part will be printed that we reject the null hypothesis. Null hypothesis says that there is no difference between the tips given at the lunch and the dinner, but this hypothesis will say that we reject the null hypothesis. So that means that there is a significant difference in the tip given. So there are significant differences between the lunch tip and the dinner tips. Okay, this is the explanation of code which I am not doing. So let us now do about the third parametric test, because I said that there are three third non-parametric tests. Sorry, there are three non-parametric tests: Mann-Whitney U-test, Kruskal-Wallis, and Spearman rank correlation. But we did not do anything about Mann-Whitney because its limitation is that it can be used only for two samples, while Kruskal-Wallis can be used for two samples, three samples, four samples, any number of groups. Okay, so it is extended form of this test only, and therefore this is just irrelevant if you can perform this. Okay. Then now we want to talk about Spearman's rank correlation. I said that Pearson correlation has one major limitation, that it is correlation for two variables which are linearly related. But what the question is what to do if the variables are not linearly related. So that means, for example, maybe this say this kind of case is there where this is my y-axis, this is x-axis, and suppose the relationship between x and y is parabolic like this, so that y is equal to x square or 5x square, some constant into x square. But in short, this kind of relationship is there. Now this is a non-linear relationship clearly. So if you want to find correlation between these two variables, that is y here and x here, then Pearson correlation will not give proper idea, because this is square, and similarly there may be cubic, there may be 4 power, there may be logarithmic relationship, there may be exponential relationship. So multiple different non-linear relationships can be possible, and in those cases Pearson correlation between the two variables, that will not give correct idea. So in that kind of case, what we do is we use Spearman rank correlation. It is rank correlation or rank order correlation, and it is a statistical measure used to assess the strength and direction of relationship between two variables when they are neither normally distributed nor the relationship between them is linear. So for Spearman test, normal distribution is also not required and linear relationship is also not required. So that is the means it is a very generalized test, because it does not compare both y and x, but it will compare rank of y and rank of x. I will tell you what is the meaning of that word rank of y and rank of x, but it will compare the correlation not between y and x, but correlation between rank y and rank x, and that is a totally different types of correlation. So therefore it is very useful in these cases where distribution is not normal, and also the relationship between y and x is not normal, or ordinal functions, etc. That type of cases are better handled by Spearman correlation than Pearson correlation. Okay. Now, one condition between for the Spearman correlation is that the function which relates the two variables, that must be monotonic. Monotonic is this kind of function where the function should be continuously increasing, or it may be continuously decreasing, but there should not be this kind of case. For example, if you have one other function, say sine curve, for example. Okay. Now, how sine curve is drawn? That those who have some science background, they are knowing that this kind of curve. Now, as soon as you see this curve, you immediately realize that the value here increases, becomes maximum, decreases, becomes zero, and increases in opposite direction, becomes maximum, decreases, becomes zero, increases in other direction again, decreases, becomes zero, and so on. So this type of curve, that is called this non-monotonal relationship, but non-monotonic function. For this kind of function, Spearman correlation coefficient cannot be used. But for this kind of function, as x increases, y goes on increasing, whether linearly or non-linearly, but it has only one direction, monotone. That means its tone never changes. Okay. Similarly, there might be a function which continuously goes on decreasing, so that is also fine. For example, this kind of function may be there, so that is also called a monotonous function, this kind of function, right? So that is also a monotonous function. But this is not a monotonous function. So Spearman correlation can be used only for this or this, but it cannot be used for this kind of non-monotonic function. Okay, that is the only requirement. Otherwise, it does not require normal distribution of data, and it does not require linear relationship between the two variables between which you are finding the coefficient. Now, the formula for this Spearman coefficient is this: 1 minus 6 into sigma di square and n square minus 1. And you don't have to worry at all. We will never find the correlation by using its formula. We will always find programmatically. There is always a simple thing to import from scipy.stats. Import Spearman rank correlation coefficient, right? And that will automatically calculate using this formula, where di is what difference between the ranks of corresponding values of the two variables, and n is equal to number of data points or observation. Now, what is these ranks? That requires some explanation. So this gives one sample data set in which originally you will be given only x and y. Okay, and these values also can be in any order. So that is, here it is a sorted order, so that it starts with the least value first and slowly goes on increasing, because I wanted to show that it is a monotonic increase in X and correspondingly monotonic increase in Y. But it might be possible that these rows are interchanged. So for X is 0, Y will be 0.1 only. Then for X is 2.22, Y will be these only. But this third, instead of third row, this might be here. Instead of this row, last row, it might be here, like that. So you have to, in short, sort it first, and then you will get this kind of order. Now, originally you will be given only this kind of data, but when you calculate the Spearman correlation, that internally first adds this kind of two columns, that is rank X and rank Y. And since the function is monotonic, now you understand why the monotonic requirement is there. The ranks are simply assigned in a proper sequence. So these are monotonically increasing. Then the minimum value is rank 1, and as the magnitude increases, you get higher and higher rank. So this is the 10th rank. And similarly, here the minimum value is 0.10, that is rank 1. And as you go 99.94, that is the higher and higher value. Okay. So roughly this is actually X and X square only, but that is some noise is added. Okay. For example, around 9 square, that would be 81, and 10 square would be 100. So it is more or less like that only, right? But some noise is there, and therefore exact values are not there. Now, in Spearman correlation coefficient, you don't get correlation between X and Y, but rather you get correlation between rank X and rank Y. And I will show you by a code that the data distribution remains almost the same, whether you plot a scatter plot of Y versus X, or whether you plot a scatter plot of rank Y versus rank X, the data distribution remains same. Okay, so that means you don't have to do these manually, right? So di is the difference between the ranks of corresponding values of the two variables. So corresponding value means this and this, and the difference between their rank is here, say 0, here also 0, here also 0, like that. Okay, but instead of that, sometimes it is possible that Y may not be exactly monotonically changing with X. So it is not Y is equal to X square, but maybe here the ranks are such that for X, this first row is rank 1, and for Y, the first row is rank 3. So the difference between them, that is this D. Okay, the difference between rank of corresponding values of two variables. Corresponding value means first row. Then suppose fifth row I take, and here for X its rank is 6, and for Y its rank is 9. Then the difference is 3. So that becomes the difference. And N is the number of data points. So here they are 10. You can take 100 or any number. Okay. So then this formula gives the Spearman correlation coefficient. Now this is a formula method, but we never use formula method. We always use program method. Okay. So what are the steps to do it? Rank the variables, and if the variables are tied, then assign the average rank. What is the meaning? Here each variable is unique, so I can easily rank them. But suppose here this is 3.33 and the second one is also 3.33. So what to do in that case? Then if this is 3.33 and this would be some number greater than 3.33, then what would be your rank? 4 and 5. So here now both have 3.33 X values in the row number 1, 2, 3, 4, 4th and 5th rows, both have 3.33. Then you will take the average of these two ranks, 4 and 5. Then average will be 4.5. And since both are same values, both must have same rank also. So you will assign rank X is equal to 4.5 for row 4, and rank Y is also equal to 4.5. So first step is rank the values of both variables. If values are tied, then assign average rank. Then calculate the difference in the rank. For each pair of data point, calculate difference between the rank of the two variables. Here in this case, the case was very simple, that the difference is 0 always. But I said that this is 1 and this is 3, this is 2 and this is 5, this is 3 and this is, say, always not 6 but 8 suppose. So for first two rows the difference is 3, for second row the difference may be 5. So you have to calculate that difference. You square the difference. Okay, so that is the di square, right? Now that so that di square is this sigma squared difference square between the ranks. Okay, so in this part the numerator says 6 times sigma squared di square. Here the di difference would be 0 all, so the numerator would be 0 only, and that means this for this kind of data set the Spearman correlation coefficient would be 1, because this part would be 0. So Spearman correlation coefficient would be 1, right? But every time the difference will not be 0. So it is possible that this is 1 and this is 3, this is 2 and this is 5, this is 3 and this is 8, like that. So the differences you have to count and square them and find the sum of squares, and divided by n square minus 1. So that is how you calculate. So that are the steps for finding the Spearman correlation. Or rather you can say that when you use this one single line of code from scipy.stats import Spearman R, at that time these steps are automatically done. So when you do this step, Spearman R, data X and data Y, at that time these 4 steps are done. So what 4 steps are done? Then this, that is, first data is ranked, difference between the ranks are counted, they are squared, differences are squared, and then summation is done. Then di square is found, then N is the number of observation. We put all values in this equation. So that when I say we put, actually the algorithm or the library which you imported, that only puts and directly gives the final value of Spearman correlation. Okay. What is its interpretation? If you get Spearman correlation 1, then you will get a perfectly monotonic correlation. For example, in this case only, this table data, you will get Spearman correlation 1 only, because all the differences are 0. Rank X and rank Y, the differences are 0. So this term would be simply cancelled and the Spearman correlation is 1. So that means that as one variable increases, other also increases in consistent manner or same manner. It is not that one variable increases and the rank is 1, then for the other rank is 4 and then the difference is 3. No, if the ranks are here 1 to 10, then here also the ranks are 1 to 10. So that means it is a perfect positive monotonic relationship. Similarly, sometimes you may get -1. So in that case, if the answer of this formula is -1, then you will say that it is perfect negative monotonic correlationship. So I gave the example. This is perfect positive correlation. Okay, and for this type of case, the correlation coefficient R is equal to 1. Now, Spearman correlation coefficient is sometimes shown by R and sometimes it is shown by this symbol. This is called rho. Okay, so whatever symbol you use, but that will be perfectly monotonic positive, and this here will have 1. And similarly, this is perfectly monotonic but negative. So here rho or the Spearman correlation coefficient would be -1. Okay, and sometimes you may not get exactly +1 or -1. You can get 0 also. So if you get 0, then there is no monotonic correlation. For this kind of graph, you will get rho is equal to 0. So there is no monotony. Okay, so it increases, then decreases, again increases, again decreases. So it is not at all monotonic. Okay, and you can get some values between 0 and 1 or 0 and -1. So that if you get 0 and 1 between them, so that means if your correlation coefficient is positive at least, but not exactly 1, but it is a 0.7. So in that case also you will say that there is a monotonically increasing correlation, but it is not perfectly monotonic. Okay, otherwise you would get rho is equal to 1. And similarly here also, if you get rho between 0 and -1, say rho is equal to -0.54. So in that case you will say that it is monotonic and decreasing type of relation, monotonically decreasing but not perfectly monotonic. Okay, right. So what value of Spearman you get, that will give you idea about the type of monotony which is inherent in your function, right? Now, what are advantages of Spearman correlation? Then we had already seen. One is it is non-parametric, so therefore it does not require assumption of normality, or it does not even require linearity like Pearson correlation. It can handle ordinal data very clearly. For example, whenever there is some hierarchy implied, I told one example that junior clerk, junior officer, senior officer, junior manager or assistant manager, manager, then maybe head or vice president of the company, president of the company, then CEO. So these kind of labels, they are ordinal. Similarly, if survey is taken, strongly disagree, strongly, then mildly disagree, then agree, neutral, agree, strongly agree. This kind of categories are there, but they also show the level of agreement in increasing order, right? So that type of cases are ordinal, and Spearman correlation is the best for handling ordinal relationship and robust to outliers. Since it is based on ranks, extreme outliers have less effect. Now that is clear because here only, instead of the value of numbers, you are just considering their rank, and the number may be very large. For example, here the last number may be there are 0 to 8.89 only, but last number may be 10,000, and similarly this can be 10,000 square roughly. But that does not make any difference. We are not finding a correlation between X and Y. We are finding correlation between rank X and rank Y. So that means this is still 10 only rank wise, and this is also still 10 only highest ranked X and highest ranked Y. So outliers have no effect on Spearman correlation coefficient, or the method is robust to outliers, right? However, at the other moment, just like there are some advantages, non-parametric, it can handle ordinal data and it is robust to outliers, there are some limitations also. One, monotony assumption must be obeyed, because otherwise your ranking itself will get wrong and less informative for linear relationship. So best thing is always to plot a scatter plot and see how your data is distributed. If you find that your data is distributed maybe like this, then it is better to use Pearson correlation coefficient only. But if you find somewhere non-linear data also we might have plotted, say this data points are distributed like this, then it might be, this is not even monotonic, okay. But yeah, this for example, this is a blue colored curve graph. So if it is that kind of data distribution, then it might make sense to use Spearman correlation coefficient, right? Okay. One more thing is here. So we saw what are the strengths and what are the limitations. What are use cases for Spearman correlation? So whenever you find that function is monotonic but not linear, in that case you can use this Spearman correlation coefficient. For example, this kind of function. Or there is one other very common function in the economics, which is called law of diminishing marginal utility, or the marginal diminishing return effect. So if you want to plot that kind, there the return is monotonically decreasing, this kind of case, right? So at that time, for modeling that kind of relationship, you should not use Pearson, but you should use Spearman. Whenever the data set itself is not normal, so then you should use always Spearman correlation coefficient. Then if the data is inherently ordinal, then some hierarchy is implied. For example, customer satisfaction survey or performance rating of employees. So at that time, you should use Spearman correlation coefficient. And feature engineering also depends a lot on this Spearman correlation coefficient, because it is a good way to handle skewed data, because Pearson can only handle normal data, so Spearman can handle skewed data also. Okay, so that much is about Spearman. And now very quickly we will draw the graph by code. Okay, first step is always same, importing the libraries, and all these are our well-known NumPy, Panda, Seaborn, and Matplotlib.pyplot. Only this is new. From scipy.stats, import Spearman R, Spearman correlation coefficient. Okay, now next step is either load the data if you have saved it somewhere in your working directory, or if you have SNS for example, then you can load the tips data also. Here I wanted to create a perfect monotonic data so that I can display the real utility of Spearman correlation coefficient. So I created a synthetic data. So I created x by np.linspace 0, 10, 100. Okay, that means this is the beginning value, this is the end value, and total 100 observations are there. And I create another y is equal to x square. So I am creating this kind of data only, that is these only, that you should understand that y is equal to x square parabolic relationship, which is a perfectly monotonic relationship. But I don't want 100% this data, otherwise a pure parabolic model will itself fit the data. So I add some random normal noise, and the scale of that noise is just 2, and the size is equal to len x. So that means in this much region, if I show that much region by some light color, then in this much region, which is equal to the length of the x, this region, I am creating noise points which are just slightly above or below this green curve, or there may be some maybe even on the green curve also, but not all. And this is my data distribution. So due to the noise, some jitter has been introduced, some trembling has been introduced in the data points, and as a result, they are now not perfectly on the green curve, but they are scattered here and there with a very small magnitude, only 2 units on either side. You are not allowing very big scattering, so that it is clear that even before I find the Spearman correlation coefficient, the Spearman correlation coefficient would be almost 1, because this data is hardly disturbed from the green curve. Okay, so it will be almost 1. Then create, so this is x and this is y, x square. Forget about the random noise, it is just added for the reason I told you. And data frame is created using the x variable and the y variable using pandas. And this is my data frame. So 0 to 10 is the x, and 100 observations are there. And 0 square plus some noise, 1 square plus some noise, 2 square, sorry, 0.1 square plus some noise, 0.2 square plus some noise. Here it is 10 square plus some noise. The noise can be negative also, so that's why 10 square is 100, but this comes out to be 99.5. Okay, here 9.9 square whole plus some noise, so it is coming out to be 98, and so on. So this is my data point. Okay, now I can plot, I will plot also in fact to y versus x, but our theory clearly says that we are not interested in x and y value. We are not finding correlation between x and y. Rather, we are finding correlation between rank of x and rank of y. Okay, so you have to introduce rank of x and rank of y. First, let us do Spearman R between data x and data y, and it will automatically convert things into, it will not automatically add the 2 columns which I showed here, and it will not measure the correlation between x and y, but it will automatically inherently inside add rank x and rank y and find the correlation between them. So if you plot it, you get the Spearman correlation coefficient is 0.99. That was expected, because I said that my data set is such that it is almost on the green line. Very little noise was added, that is np.random.normal with scale only 2. Okay, so that scale is just a little bit jitter is provided with respect to the green curve, and therefore it is almost monotonic, and therefore I get the Spearman correlation 0.99. Okay, and p value is 0. Okay, so p value is 0. That means null hypothesis can be rejected. Null hypothesis would say that rank x and rank y, they have no significant difference here. But clearly here x is x and y is x square, so rank x and rank y will have significant difference, right? Now if you visualize the data, you get more clear idea. So what we do is first we plot a scatter plot of x versus y. Okay, and that is how to plot. That is our usual method: plt.figure, plt.plottype, plt.title, plt.xlabel, plt.whitelabel, plt.grid, and finally plt.show. And this is y versus x plot. rank, no, not this one. Okay, so let me clear this output first. Okay, so this is the y versus x plot. On this axis this is y, and on this axis there is x, and it is nearly parabolic because y is equal to x square plus some noise, x square plus some noise. But let us plot y rank, then that will explain why the method of Spearman correlation works, because I am not finding correlation between x and y, but I am finding correlation between rank x and rank y. Still, the distribution of y versus x and the distribution of rank y versus rank x should be same. Then only it will work, right? So we will now plot a graph of rank y versus rank x. So data x rank, I am creating one this kind of column is equal to data x dot rank. Okay, where what is data x? That is x column of my data. This is my data, pandas data frame, and it's x column. But now I am saying dot rank. So now I am not taking the absolute value, but I am taking its rank. Similarly, data y dot rank, where what is data y? This is my data, and this is the y column. So I am taking the rank of each observation, and then I plot a scatter plot only. But previous was scatter plot of data x versus data y on x and y axis, while this is scatter plot of data x rank versus data y rank. If I write one more line here, print data, then you will understand that two more columns have actually been added in my data. Okay, so I take the rest of the lines in the next cell, and let me first print the data. Now you can see x, y, rank x and rank y. Okay, so you get these, and now I am earlier plotted, I plotted this scatter plot, x versus y or y versus x. Now I am plotting this scatter plot, rank y versus rank x, and it comes out to be like this. You can see that its nature is more or less same as this. It also shows monotonic increase. Of course, it is not exactly that parabolic type of shape, because it is the relationship between ranks, and ranks are just 1, 2, 3, 4 and 11. Here you can see the difference also, that the difference is not coming out to be 0. The example which we took, that is this. Here the rank x and rank y were always equal, and therefore the difference came out to be 0. But here the difference is not exactly 0. The difference is here 6, here it is 3, here it is 10, here 15, and so on, right? So difference is there, and therefore I will have, I means this algorithm internally, when I use this Spearman R, it internally calculated rank x, rank y, and it internally applied that formula. Where is that? Yeah, this formula, and calculated the correlation coefficient. So the reason why Spearman correlation works is because whatever is the distribution of y versus x, same monotonic nature is seen in the distribution of rank y versus rank x, provided y versus x relation in the beginning, right from the beginning, that itself is monotonic, and there is no need of normal distribution or anything, right? So we got Spearman correlation 99599. So that means that this is a strong monotonic positive correlation between y and x. Okay, and p value is less than alpha, so that means that null hypothesis is rejected. Now here these are exercise question, and again